Everything in the world around us is made of atoms, from the ground we walk on, to the air we breathe, to the water we drink. We aren't usually aware of the atoms because they're far too small to be visible. If we could see them, we'd find that water is made of hydrogen atoms and oxygen atoms, for example. So how do we know that everything is made of atoms? Until recently, scientists could only suggest, based on their experiments, that substances were made of atoms which are combined in fixed proportions. It's only in the last 40 years or so that we have developed extremely powerful microscopes which can image the individual atoms in a substance. These are gold atoms, and we can see that pure metals such as gold have a layer structure. There are so many different substances in our world that it can be a surprise to find out that they are all made up from just under 100 naturally occurring types of atom. Each type of atom is called an element, and these are recorded and ordered in the periodic table. The URL below will take you to an interactive website where you can see images of these elements and find out more about them. It is perhaps even more surprising to find out that all these different atoms are made from only 3 components called subatomic particles. Each atom has electrons surrounding a nucleus, which contains protons and neutrons. Each of these subatomic particles has different properties. Protons and neutrons have the same mass as each other, and electrons are much lighter. It is important to learn and remember that protons have a positive charge, and electrons have a negative charge. Neutrons are not charged particles. This means that all the positive charge in an atom is in the nucleus, and all the negative charge surrounds it. Atoms overall are not charged. This is because each atom has the same number of protons and electrons, so the charges are balanced. What makes atoms of one element different from atoms of another element is the number of protons. Each different element has its own unique number of protons. For example, phosphorus atoms on the left have 15 protons, and sulfur atoms on the right have 16 protons. Any atom that has 15 protons is a phosphorus atom. We call this number the atomic number or proton number. When we look at a periodic table, we find that the elements are in order of atomic number, starting with hydrogen, which has 1 proton, then helium, which has 2. Here we can see phosphorus and sulfur. Notice that for each element, the atomic number is the smallest of the 2 numbers shown. Because the electrons are so much lighter, it is the protons and neutrons together that give an atom its mass. We call the total number of protons plus neutrons the mass number. So this is the number of particles in the nucleus of an atom. To completely describe an atom of an element, we use a symbol which is 1 or 2 letters long. The first letter is always a capital, and if there is a second letter, it is always lowercase. We then add the atomic number, which is the number of protons, and the mass number, which is protons plus neutrons. If we're given information about an atom in this form, we can easily say how many protons, neutrons and electrons that atom has. The number of protons is equal to the atomic number. The number of electrons is the same as the number of protons, and the number of neutrons can be found by subtracting the atomic number from the mass number, so that protons plus neutrons take away protons. Atoms of different elements can have the same number of neutrons. It's only the protons that give atoms their identity. Pause the video now and have a go at working out the gaps here. You'll need a periodic table. Pause the video again and you can check your answers. Not only can different atoms have the same number of neutrons, we can also have atoms of the same element that have different numbers of neutrons. We call these isotopes. For example, Atoms of hydrogen always have one proton. Most have no neutrons, but some have one or even two neutrons. These isotopes of hydrogen have the same chemical properties, but will have different masses. Because atoms of the same element can have different masses, we can work out the average mass for an atom of an element. We will need to take into account all the different naturally occurring isotopes of that element, and how much of each there is, which we call the abundance of each isotope. These average masses for atoms are called the relative atomic mass, and these are the other number shown for each element in the periodic table, along with the atomic number. We need to define a scale so that we can compare these average masses, so it has been agreed that the relative atomic mass of atoms of the carbon-12 isotope will be exactly 12, and we compare all other relative atomic masses to this. You may notice that some relative atomic masses shown in the periodic table are not whole numbers. This doesn't mean that an atom can have a fraction of a neutron. Remember, these are averages. If we know how much of each isotope we have, then we should be able to calculate the relative atomic mass for any element. For example, here is the percent abundance data for chlorine atoms. We calculate the relative atomic mass, which has the symbol A subscript R, by multiplying the abundance by the mass number. As the abundances are percentages, we need to divide these by 100 to get them as fractions. We do this for each isotope, then we add the results together to get the relative atomic mass. We can see that this value matches the one shown in the periodic table. Now you can practice. Here's the isotopic abundance data for magnesium. Calculate the relative atomic mass to 2 decimal places. Pause the video, then have a go. Here's the working out. Pause the video to check your working if you didn't get 24.32. Sometimes, instead of percent abundance, we may be given relative abundance. The numbers show how many atoms of each of the other isotopes you'd have if you had 100 atoms of the most common isotope. For example, for every 100 chlorine 35 atoms, you'd find 33 1/3 chlorine 37 atoms. We can use data in this form to work out relative atomic masses too. We need to multiply each isotope's mass number by the relative abundance and add up these values for each isotope. Then we need to divide the result by the sum of the relative abundances, which is the total number of atoms of all the isotopes. We get the same answer as we did with the percent abundance data, which is reassuring. We often see different illustrations showing electrons around the nucleus, but we must remember that these are models to help us explain how atoms work, and that atoms aren't really like this. Electrons aren't really tiny marbles whizzing around the nucleus. The most useful model for us at GCSE is the one on the left. Here the electrons are shown arranged in a series of shells or energy levels around the nucleus. Each shell has a limited number of electrons it can hold before it's full, and the shells are filled from the innermost outwards. The lowest energy level is the innermost shell, and the energy levels get higher as we go outwards from the nucleus. It will be important for our understanding of reactions to appreciate that the nearer the electrons are to the nucleus, the more strongly they are attracted, and the more difficult it is for an atom to lose them. The innermost shell, sometimes labelled n equals 1, can contain a maximum of 2 electrons. After that it is full and electrons go in the next higher energy shell. This can hold 8 electrons before it becomes full. The third shell can also be filled with up to 8 electrons before the fourth shell starts to be filled. Using these rules we can work out where the electrons will go in any of the first 20 elements of the periodic table. For example, the periodic table tells us that a sodium atom has an atomic number of 11. This means it has 11 protons and therefore 11 electrons. We can start filling these in according to the rules. Now the innermost shell is full and electrons go into the n equals 2 shell. When this shell is filled with 8 electrons, the final electron goes into the third shell. If you're interested, you can do some research on what happens to the electron arrangements after the 20th element, calcium, as we start to go through the transition elements. You'll find that the basic rules we've used here need to be extended, but you don't have to understand this at GCSE level. It's not always convenient to draw all the circles and electrons, so we can also use a notation where we list the number of electrons in each shell, innermost to outermost. For the chlorine atom, shown here, we'd write 2, 8, 7 as the electronic structure. So we can write or draw the electronic arrangements for the first 20 atoms. If we look carefully at these, we'll see some important relationships between electron arrangements and where elements are in the periodic table. See if you can see what all the elements in any group have in common. See if you can also see what all the elements in any period have in common. Remember, groups are the vertical columns in the periodic table, and periods are the horizontal rows. Hopefully you noticed that all the elements in a period have the same number of shells in total. For example, everything in period 3, sodium, magnesium, aluminium, etc., has 3 shells. You may also have noticed that every element in a group has the same number of electrons in its outermost shell. You may have noticed that the number of outer shell electrons is the same as the group number. All the elements in group 1, hydrogen, lithium, sodium, potassium, have 1 electron in their outer shell. These patterns will help you remember how to draw or write the electron arrangements for these atoms if you look at a periodic table. Now that we know what we need to about the atoms themselves, we can start to study how atoms are chemically bonded together to make different substances. We can have elements that are made of only one type of atom, or we can have compounds which are made from more than one type of atom. Compounds are not just mixtures of atoms. In a compound, the atoms are chemically bonded together and can't be separated by physical means such as filtering or distillation. We find that atoms bond together to form 2 different kinds of substances. We can have individual small groups of atoms, each group identical, which are called molecules. Here are some water molecules. Each contains an oxygen atom, chemically bonded to 2 hydrogen atoms. There are no bonds between the molecules, each is separate from the others. Other substances are giant 3-dimensional structures with chemical bonds linking all the atoms throughout. Here's the tip of a diamond, showing how the carbon atoms are chemically bonded into a giant lattice. Every substance has a chemical formula, which tells us which atoms are bonded together in the substance, and how many of each. The formula makes use of the element symbols shown in the periodic table. The simplest formulae are for the elements, as these only consist of one type of atom. For most elements, we can just write down the element symbol, and that's the formula of the element. A few elements consist of pairs of atoms chemically bonded together. For example, the oxygen we breathe consists of O2 molecules, each molecule being made from 2 oxygen atoms bonded together. The mnemonic HF Bronicle helps us to remember which elements consist of pairs of atoms and needs a subscript 2 after the element symbol when writing its formula. Hydrogen is H2, fluorine is F2, bromine is Br2, etc. The formulae for compounds are a list of the types of atoms present, followed by a subscript number to show how many of that atom if it's more than one. The formula NaF for sodium fluoride shows us that it contains Na and F, and that there is one of each atom present. The formula for phosphorus trichloride shows us that it contains P and Cl atoms. We can expand this formula out to make a list of the atoms present. There is one P atom, and the subscript 3 shows us that there are 3 Cl atoms. The formula for sulfuric acid is H2SO4. We can see that there are 2 H atoms. A common mistake is to think that there are 4 SOs. Remember, each new element starts with a capital letter, so S is the next element, not SO. As there is not a number after the S, there is one S atom. Now comes O, and the subscript tells us there are 4 O atoms. Here's the formula expanded to a list of atoms. We can see that there are 7 atoms in total in a sulfuric acid molecule, and that they are of 3 different types. Some formulae use brackets. The number after the brackets applies to everything inside the brackets. So, for barium hydroxide, we have 1 Ba, then we have 2 of both the O and the H. So the expanded list of atoms is BaOHOH. There's 1 Ba, 2 O, and 2 H. Here's a more tricky formula for ammonium sulfate, but the same rules apply. Inside the brackets, we have an N and 4 H's. The 2 after the brackets shows us that we have this again, another N and 4 H's. Finally, we have an S and then 4 O's. So in total we have 2N, 8H, 1S and 4O. Now that we know how to take a chemical formula and work out exactly how many of each atom is present in that substance, we can use our earlier knowledge about the masses of atoms to work out relative formula masses. These are extremely useful in chemistry. The relative formula mass is the sum of the masses of all the atoms in a substance as shown in its chemical formula. For example, the formula of water is H2O, so we know that water has 2 H atoms and 1 O atom. We also know from the periodic table that the relative atomic mass of a hydrogen atom is 1, and that the relative atomic mass of an oxygen atom is 16. We can therefore work out that the relative formula mass of water is 1 plus 1 plus 16 is equal to 18. Here are the chemical formulae of 5 compounds. Pause the video and use a periodic table to work out the relative formula mass of each. Remember, when you're finding the relative atomic masses on the periodic table, that these are the larger of the 2 numbers given. The other is the atomic number, and you don't want that. Check the key on the periodic table if you're unsure. Here are the answers. Pause the video to check your answers and check your working for any that you got wrong. In our next topic, we're going to see how the chemical bonds in different substances work and how the different kinds of bond lead to different properties, such as high or low melting points and boiling points, or being able to conduct electricity.